Everybody. I'm delighted to introduce this week's speaker, Olivia Cooper. So Olivia did her undergrad at Smith College and then went to UT Austin for grad school. She's currently a fifth-year graduate student and an NSF research fellow. She's broadly interested in massive galaxy evolution at high redshift and is an expert in dusty galaxies, the submillimeter and beyond, and how to connect this long wavelength data with all of the amazing stuff we've been finding with JWST. She leads the Searching Far and Long survey, which I'm sure that we'll hear about today, and also co-founded the Astrobites Climate Change Committee and is co-chair of the Outreach Committee for Cosmos Web, which is one of the big JWST collaborations. So let's welcome Olivia.
Thank you, Red. Awesome. Thanks everyone for having me. Yeah, I'm excited to talk to you today about all things dusty galaxies. We're going to look at a lot of cool data, tell you about some of the cool projects I've been involved in lately, and some of the current challenges with studying dusty galaxies. So I want to start with this sort of overall view of what my research is about, which is looking at the assembly of the cosmos in general through the lens of star formation in massive galaxies. The reason we're thinking about star formation, it is the major driver of the transformations going on in the universe, especially at early times. And I spent way too much time on this Canva graphic over the summer. If you haven't used Canva, it's fun for stuff like this, just to show some of the transitions that are going on in this sort of graphical sense. Thinking about the first stars turning on and some of the first galaxies reionizing the universe, building up more complex molecules, dust and metals, and then eventually these larger massive galaxies, elliptical galaxies, clusters of galaxies, and all the star formation going on within them, assembling all the different components of the universe. And in a more quantitative way of thinking about this, we can think about the two eras of the universe split into the era of gas accretion and gas depletion. And one way that we've traced this is by looking at the different components of mass, the different baryons that make up the universe. So if we split this into stars and the cold gas, so the fuel for star formation, you can see that in the first 2 billion years or so, starting from the onset of some of the first galaxies beyond redshift 8, to coming towards the peak of star formation in the universe around cosmic noon, redshift 2, you can see that while we don't have a ton of constraints on the nature of the ISM, the cold gas, the fuel for star formation at higher redshift, we do have, by nature, an ISM-dominated or cold gas-dominated universe. Then this cold gas is getting condensed into stars, and we start to enter this peak of star formation activity in the universe in the era of gas depletion, where the stellar mass starts to dominate the total baryonic accounting of the universe. Some of the big questions that I think about in my research in terms of looking at this transitioning universe from the era of gas accretion being ISM dominated to the era of gas depletion and stellar mass dominated is thinking about how the structures, how the galaxies, how all the different components of the mass formed so efficiently, when and where those efficient conditions were happening. How did we drive these extreme starbursts? How did they eventually get quenched so rapidly? How did the first dust form? So these are some of the motivating questions in my research overall. And in trying to answer these questions, I think two of the major roadblocks that we're working on solving with data like coming from ALMA and JWST is we currently lack complete samples, especially of the dust-obscured universe where most of the star formation is happening. And we're missing key physics driving these phases of rapid assembly, rapid efficient starbursts, rapid quenching. So I think these are some of the most important areas to start to fill in both complete sets of data and also very detailed data. So I'm going to go through two sort of branches of this talk. One is the emergence of massive galaxies, specifically dusty galaxies, and later we'll talk about their evolution a little bit more. So I want to actually take a step back. So we started getting into some quantitative plots, but I want to orient all of you to massive galaxy evolution as a concept and where we started even before most of the students in the room knew about astronomy at all. It's actually not been very long since we've had deep field images. And so I want to show you one of the very first deep field images that existed, this far out of the way, which is from 1990. And this is what it looked like. This is what we were working with really not that long ago, if you think about it. And you know, we had our goals set pretty high in terms of what we were going to find in these ground-based or near-infrared images. It's actually interesting to look at these old papers, and I think, you know, the consensus was, yeah, there's other galaxies, we know about them, but probably the most distant ones don't matter that much. But we'll probably find them out to like redshift 20. Not really finding redshift 20 in this image, but in theory, yes, the K-band is sensitive, not from the ground. We're still working on that redshift 20 limit, but you can see that even in 1990, the aspirations were there. And from then until now, the progress has been pretty astounding. So this is the Hubble Ultra Deep Field, probably an image many of you have seen before. A few decades later, and images like these have really transformed the field of galaxy evolution. We've found thousands of galaxies across cosmic time in these little patches of the sky. And if you guys are familiar with the story with HST and the deep fields going on with that, it was sort of a risk to point a telescope at the sky for such a long time. What are you going to find in this like blank field? And as we all know now, it was rich with distant galaxies. But even this deep field picture is not encompassing the whole story. I like to overlay the ALMA image of the Hubble Ultra Deep Field, and I'll sort of blink back and forth. You can see there are galaxies circled in red that were completely invisible in the Hubble Ultra Deep Field that start to pop out in the ALMA image. And these are actually sites of massive ongoing star formation and account for a lot of the stellar mass buildup, especially at that peak of star formation in the universe, that we were just completely missing with even this really deep image with Hubble. So that big picture still doesn't even capture the full picture of star formation and massive galaxy evolution in the universe. And this is a key concept of my work, is that if we're limited to the OIR, to the optical, we're missing at least half of all star formation in the universe. And so it's really important to get a multi-wavelength view of galaxies and star formation across cosmic time. So that brings me to the submillimeter. So in far infrared wavelengths, we've also taken these deep images and wide images, and that's led to the discovery of thousands of these massive dusty starbursts that I showed before in the ALMA image. And similar timeline of those first deep images that we saw from the 90s. We're taking submillimeter maps of the universe and finding that a significant fraction of star formation in the universe was missed from these optical surveys that was now popping up in these submillimeter wavelengths. And this led to decades of discovery, building up these samples of thousands of massive dusty starbursts with instruments like SCUBA, Aztec, and from Spire on the Herschel satellite. So what did these papers find from these submillimeter galaxies? What is the dusty star forming galaxy as a population? By building up these large samples and then following them up with other wavelengths, spectroscopy, et cetera, generally characterize the population of dusty star forming galaxies as having these extreme dust reservoirs, which is characteristic of their submillimeter detection. As they are discovered in the submillimeter, they're bright due to dust heated by their star formation and obscuring the optical light. Hand in hand with those massive dust reservoirs is the ongoing star formation that's producing all that dust. Some of the most star-forming galaxies that we know to exist. And to produce that much star formation, they have to have a lot of gas. So they're also extremely rich gas reservoirs that are depleting their gas very quickly to support all of that ongoing star formation. And then tying that all together, they're extremely massive in terms of their stellar masses and are often some of the most massive galaxies that we see across redshifts. As a population, again, by doing this multi-wavelength counterpart identification, looking to other wavelengths, trying to get spectroscopic redshifts for things, we found that the population of dusty star-forming galaxies really peaks at cosmic noon, at that star formation peak. So this is a plot, if you work in galaxies, you've probably seen many, many times. The star formation rate density over time. So we have redshift on the x-axis, and basically how many stars you're forming as a density on the y-axis. And you can see the measurements from these UV or optical galaxies that we're seeing with Hubble in blue, pretty well characterized out to even really high redshifts. And now we're doing an even better job with that with JWST. With the submillimeter, you can see this obvious peak at redshift 1 to 3 that are actually more dominant than the UV optical galaxies we're seeing with Hubble, but it becomes very uncertain beyond that peak. And this is sort of the needle in a haystack problem. These galaxies are very massive, very rare, and become more and more rare past redshift 3 or 4, with only a handful of dusty star-forming galaxies known beyond redshift 5. So we, due to these sort of observational challenges, we don't have a good handle on the volume density of these dusty star-forming galaxies beyond redshift 3. We have a sense that they do peak at redshift 1 to 3. But beyond that, we don't have a handle. They seem to be rare. We don't know how rare they are. We don't know when they started popping up. They're fairly evolved to have so much dust. So when are the first dusty star-forming galaxies? How common are they? When do they start to dominate over the Hubble sort of detected galaxies? These are all yet to be answered questions. And because of this needle in a haystack problem where they're rare and completely dominated by the population of dusty star-forming galaxies at redshift 1 to 3, we don't really have a good handle on what DSFGs are like beyond redshift 3 and what the population is like. So how do we start to get at this problem and take an efficient census of dusty starbursts at high redshifts in order to understand how they contribute to the star formation rate density? When does the first dust come on? What is the population like as a whole? One of the solutions is to go to longer wavelengths. So this is a really key plot in my research, just showing the different ways of selecting dusty star-forming galaxies. So similar to the plot I showed before, we have redshift, and then instead of star formation rate density, it's the number density. On one of the y-axes and on other y-axis with the colorful point lines, we have basically a sensitivity curve. So we want to compare this to the 5 sigma detection threshold for all these different wavelengths of detecting these submillimeter galaxies, these dusty star-forming galaxies. So starting with the blue curve, this is Herschel at sort of the classic submillimeter wavelengths, 250, 350, and 500 microns. And you can see it really drops off for galaxies beyond redshift 2 or so. So we're really not sensitive beyond that peak. Then if we go to the green curve, we have the SCUBA selection. This is the standard way of selecting for submillimeter galaxies. So at 850 microns or so, and you can see this curve is characteristically flat. This is due to the strong negative K correction, if you remember from any of your classes. Basically what this means is a redshift 1 DSFG looks the same as a redshift 10 DSFG at these wavelengths. So we really can't pick apart these populations, and it's going to be totally overwhelmed by this peak of the number density at redshift 1 to 3. Then if we go to longer wavelengths like this orange curve, you can see that we have this turnover where the sort of taking the strong negative K correction to an even further extreme, you have this turnover at high redshifts where you're more sensitive to the high redshift objects than the dominant population. And you effectively are filtering out the low redshift DSFGs by using all these wavelengths in combination, specifically the SCUBA wavelengths, so the standard submillimeter detection technique, with the longer wavelengths from ALMA 2 millimeter, for example.
Okay, great.
Yeah, so it has to do with the sort of redshift dependence of the brightness. And so I think the most important takeaway for this plot is that as the SED of the galaxy is shifting through wavelengths due to the redshifting of the galaxy, as you're probing different parts of the SED, the shape of it is making it so that the flux you're gathering is approximately constant, even though the galaxy is getting further away and then fainter. You're moving up in the flux of the SED effectively. So this has been done before in a blank field way. So similar to these Hubble deep fields, if we use ALMA as a mosaicing sort of deep field instrument, which it's sort of expensive to use it in that way, but we can. This has been done before with the MORA survey, map beyond obscuration to reionization with ALMA, and this was specifically designed to search for these high redshift DSFGs by making a 2mm map. And it was pretty successful and led to the extended MORA survey, which was recently on the archive. And these two surveys together, we have nearly 0.2 square degrees field within Cosmos, and it found 37 sources detected above 5 sigma. So these are predominantly high redshift DSFGs, pretty good at finding the high redshift population beyond 3, much higher median redshift than the sub-millimeter surveys were able to capture. And one of the most exciting parts of this survey is it was starting to put constraints on the volume density out to higher redshifts. You can see the most important part in this plot is the previous constraints in the sort of neon green are just whopping sort of orders of magnitude discrepant past redshift 4. And with the MORA survey starting to put tighter constraints on the volume density of these massive galaxies at those redshifts. But one limitation is how expensive this survey is, taking nearly 30 hours with ALMA. It's nice, it's unbiased, you don't have any prior information about the galaxies, you just go out and detect them in the 2mm, but we put together a fairly large map and just found these 30 sources. One thing that is interesting to keep in mind is that all of them, nearly all of them, there's a few exceptions, were detected with SCUBA. So we already knew about them with these big sub-millimeter maps that we've had for decades. So this, like Ren mentioned, the Searching Far and Long program that I'm leading is basically the same concept, using this 2mm wavelength to find these high redshift DSFGs, but do it more efficiently by starting with the sub-millimeter maps we already have had for decades. So this is the concept of searching far and long, using these targeted 2mm pointings really efficiently to do a first order redshift sorting of dusty star-forming galaxies over much larger samples than we were doing with these blank field experiment. Really simple criteria, just target all the bright sub-millimeter things that are in ALMA fields, and it takes less than a minute per source. So very efficient, it's what ALMA was designed to do. So the pilot study was out a few years ago. It was interrupted by COVID, and so I had a smaller sample to work with only about 40 targets. But I found this, although it's a loose correlation, as expected based on our empirical modeling, this ratio of flux density. So on this plot, we have redshift and flux density ratio from the SCUBA wavelength and the new 2mm data point. We can see that generally you can have this redshift sorting where the higher redshift sources have a boosted 2mm flux density, and so they show up lower to the lower right side of this plot, where a lower flux ratio tends to have a higher redshift for these objects. Much more efficient than the MORA survey could do, and one of the most efficient ways to find these high redshift DSFGs in general. And so I mentioned that it got interrupted with COVID. We went back and asked ALMA for some more time, and thankfully they gave it to us since we expanded the survey by 10 times. So now we started with the SSA22 field. In the background are just the SCUBA maps in the sub-millimeter, and then you can see all the targets that I pointed in purple in UDS and Cosmos compared to a few of the JWST fields. So we have Primer and UDS and Cosmos Web. I'll talk a little bit more about those later. In green. And then you can see the coverage of the Ex-MORA field. So the Searching Far and Long program has the advantage of going much wider than Ex-MORA. And then I'll talk about SCUBADive a little bit later as well, another survey of these DSFGs within the Cosmos Web field. So here are the results from the full program from my paper in prep, showing for much lighter sample the same plot. You can see we have a lot more species, and also the advantage of JWST photo-Zs, which were a lot more constraining than the far infrared photo-Zs. You can see this relation holds, although there's still a lot of scatter, there's a lot of degeneracy that's being encapsulated in this plot. You have this first order redshift sorting where you can really quickly identify what the high redshift candidates are from this sample of nearly 400 targets, or nearly 500 targets, really. So I've presented to you some of the candidate first DSFGs ever. We're starting to fill out the volume density of them at higher and higher redshifts. And then I want to move on to this other concept, which is, okay, now that we're finding the highest redshift DSFGs, can we look more in detail about how the population of DSFGs is evolving, look at individual galaxies, and probe their star formation and dust characteristics in a little more detail. This is basically what I said. To get this detailed perspective, we need multiple wavelengths, looking at the stars and the dust and the gas. And this is where the ALMA plus JWST combination is really leveraged. So sticking with the Searching Far and Long program for just a moment, these are 8 of the sources that I targeted. These are the Cosmos web cutouts, so JWST imaging of some of the sources, and then red are the ALMA contours. So you can see one sort of quick test whether or not Searching Far and Long worked is the stronger ALMA 2mm detection, so more contours on this plot, tend to be the higher redshift sources. The redshifts are listed for each one. So for example, this is a high redshift one beyond redshift 4, versus low redshift ones that are less strongly detected with the ALMA 2mm. The other thing I want to point out about this is the diversity of morphologies from these DSFGs. So this is something we've known about before, that there's heterogeneity in the population of submillimeter galaxies, but that's something we haven't been able to see in quite this much detail until now. So some of the characteristics I want to point out, like their low redshift counterparts, we expect to see some mergers triggering these huge bursts of star formation and then their subsequent dust emission. We also see a lot of clumpy star formation that before JWST, we couldn't quite see that much detail. Then we also see these big isolated disks. So instead of the big merger triggering the star formation, you can see that in some cases, this huge burst of star formation is triggered by just cold gas accretion and turbulent disk instability based on their morphologies. This has been shown before over the past decade, that we know these galaxies are physically heterogeneous. And so this is bringing new detail to this expected result. And one of the other works that I mentioned before, the SCUBADive project, this is our logo for the team. You have to have, you might recognize some people you've met before. And then Jed leading the project is in the middle there. Jed McKinney at UT's postdoc. The SCUBADive project is really focused on this detailed characterization and is specifically selecting the submillimeter galaxies, so SCUBA selected, that have ALMA pinpointing, so we know very precisely where they are, and then also within the JWST coverage of Cosmos Web. So there are about 700 submillimeter galaxies within the footprint of Cosmos Web, which is shown in blue over here, and nearly 300 of them have ALMA coverage, so that defines the sample. I think the story goes that Jed was on a plane to AAS, and he slapped the SCUB contours on the new Cosmos Web images that had just arrived, and found this one crazy source that was really faint in JWST, and that started the whole SCUBADive project. So it really demonstrates why this multi-wavelength approach is so cool. You're seeing galaxies that we'd known about the submillimeter blob for a long time. We did not know that it was at redshift 6. The JWST imaging is giving us that insight, that we're finding this really high redshift little red blob in the imaging that was just totally absent in the HST and ground-based imaging before. So Jed started out with this paper on this one source, Aztec 71, has now expanded the sample to nearly 300 galaxies, doing really tremendous work. Now we have this really detailed view of the stellar content of dusty star-forming galaxies, including a large sample of OIR dark galaxies that we had not previously seen with HST and ground-based data in the field. So there's, all 300 you can find on his paper, but I just wanted to show you a few of these dusty star-forming galaxies, just really emphasizing the point that the sample of some millimeter selected galaxies isn't totally not uniform. We're getting a lot of different types of galaxies represented in the sample. And so this is one of the coolest ones, this like huge grand design spiral, this crazy merger. That's a sub-millimeter galaxy. We're getting this impressive detail with the new JWST imaging. Then you have these like probably high redshift, like tiny faint blobs, a lot of clumpy star formation, some low redshift things, some disky things, a really incredible diversity of morphologies in the sample. Yeah, watch out for more papers from the SCUBADive project. There's a lot of work to be done with this really cool sample. So I want to take the level of detail one step further from JWST imaging to go into spectroscopy. This can really enable detailed understanding of the star formation conditions, the sort of evolutionary phases of dusty star-forming galaxies, and also the conditions of the dust within them. So just taking a step back and talking a little bit about where we started with spectroscopy of DSFGs. This is from my advisor, Caitlin Casey's paper from 2017. This is from the Mossfire instrument with Keck. It was a challenge to get spectra of dusty star-forming galaxies in the optical. Two major issues. One is without ALMA, which was at this time, we didn't have a ton of ALMA coverage yet. We didn't really know which galaxy corresponded to the massive sub-millimeter blob, this really like blurry image in the sub-millimeter that we had. It was hard to figure out which galaxy in the optical to associate it with. So relatively low yields from spectroscopic surveys due to this OAR counterpart uncertainty. The other issue was without a ton of constraints in the optical from imaging, we had a huge uncertainty on their photometric redshifts. Like I was mentioning before, it's hard to get a photometric redshift of a DSFG without either this longer wavelength data, both in the far infrared and the optical. And so what we were working with pre-JWST was pretty minimal. And you'd go out and observe hundreds of DSFGs, or at least what you thought were the right galaxies, and get relatively low yield spectroscopically of like 30%. And maybe you would detect just one line and it was very faint. So it was a hard game to play. But you know, Caitlin's work produced this stack of the sort of typical sub-millimeter galaxies, redshift 2 DSFGs. This is about 20 or so stacked together. You can see, of course, they're starbursting, so you're getting these nebular emission lines, and they're dusty, so you're getting this, you can see by eye, Balmer decrement, where you have strong H alpha and hardly any H beta, if at all. So this is kind of what we were working with before JWST. And you can see the sensitivity, the wavelength range, all that really changed with the NIRSpec instrument on JWST. So over the summer, I was in Copenhagen at the Dawn Institute, Cosmic Dawn Center, working with a few people there. And the project that we came up with for me was to cross-match the ALMA sources we knew about and see if any spectra were already taken and publicly available on the Dawn JWST archive that Gabe Rammer and his team have put together. You can basically just search any of the publicly available imaging and spectra. So I set out to do that, see if there are any ALMA detected sources that had spectroscopy already from various programs. And there were 5. And so I'm showing just overlaid on the SCUBA map. There were 4 at this sort of typical cosmic noon redshift and 1 high redshift one. They all happen to be from this program called RUBIES, which was specifically targeting bright red things at high redshifts within a few JWST legacy fields. So today I'm just going to focus on the cosmic noon sources. They kind of tell an interesting picture of the evolution of DSFGs, but you know, watch out for the high redshift one. It's also cool, but I'm not going to talk about her today. Okay, so starting with their photometry, all 4 of these, we've known about them for a while. They're classic sub-millimeter galaxies. We have their ALMA fluxes, so we know that they're bright in the sub-millimeter. They're sort of typical. They have indistinguishable photometry, the 4 of them. So you can see in their rest optical SEDs, they're rising in red, so they're dusty. They're pretty bright. They all have these huge stellar masses above 11. And again, all have these redshifts around 2.5. And these have been studied before from the ALMA perspective, and combining that with ground-based data and HST data, they're sort of not special. They just look like normal dusty star-forming galaxies. They're right in the submillimeter. They're very red. They're very massive. They're very star-forming. So just your run-of-the-mill submillimeter galaxies. But if we look at the spectra, the picture starts to get a little more complicated. So starting with the two at the bottom in purple, these kind of look like what we expect from star-forming galaxies, especially dusty star-forming galaxies. They have a lot of nebular emission lines. They're rising in red, and they have these big Balmer decrements. So that's indicative of the dust content within these galaxies. Similar story for this galaxy up here in purple, still very star-forming. You have that strong H alpha with no H beta, so very star-forming and also very dusty. You can see that it's the slit, so the where the spectra was taken is extended across the galaxy. So that is why the shape is a little more wiggly. We're actually capturing multiple components of the galaxy in the spectrum. And then my favorite galaxy in the sample is the one shown in green. It looks pretty different from the other galaxies. Still has this H alpha emission, still looks very dusty, but it uniquely has this very clear Balmer break. And that tells us that the stellar population is more evolved, and it's starting to have its star formation shut down. So the more massive stars have started dying off, and we're starting to get the dominant population contributing to the stellar light as a more evolved stellar population. And so instead of a dusty starburst, it's probably more appropriate to call this a dusty post-starburst. This is not entirely surprising given how diverse the morphology is. We knew that submillimeter galaxies were comprised of a few different types of galaxies, but this is not something we've ever seen before, that it could still be bright in the submillimeter and have this evolved population start to be shutting down its population, and yet it would still show up bright in its dust emission. So I'm going to come back to that point a little bit later. Another thing that was really cool to see in these spectra, so before with the ground-based spectra, we maybe had like a few lines to work with. Now we have over 10 lines per source that are strongly detected, and there's a lot of interesting physics we can do with those lines. This was my first, I'd worked with spectra before, but not with this much detailed information. I actually had to look up what a lot of these lines were because I was not familiar with, for example, this iron line. So I had to ask around, but I've identified all of them, and now we can play with them in a little more detail. And so what I'm showing here is an attenuation curve. So apologies, I've cut off the wavelength axis, but basically just the wavelength extent of the spectra. The stars are showing the data points, so using all the different Paschen and Balmer decrements to probe the dust content of the galaxy. So starting from Paschen beta and going all the way to H alpha and H beta, we're using these line ratios to characterize how the dust is attenuating the light in the galaxy as a function of wavelength. This is a process or an analysis that has been done before for local galaxies and for the Milky Way, and for local starbursts at redshift 0. If you've heard of the Calzetti curve, this is what is shown in this darker gold color. So this is a relation that we usually just slap on to our analysis of galaxy SEDs based on local relations. We have very little constraint at high redshift. And so I'm showing a couple of the measurements that have been made beyond redshift 0. So for example, from ground-based spectroscopy, a stack of all these redshift 2 regular star-forming galaxies is shown in yellow. And then a very recent paper on the archive for one redshift 4 star-forming galaxy is shown in black. So one thing I want you to notice from this plot is that the attenuation curves do vary across the different tracers. So the different ways of measuring it from the Milky Way is different from the SMC and LMC. That's giving us a sense that the dust in these different environments is different in some way, either the geometry or the position of the dust. And then another interesting thing is that it potentially has an evolution across either galaxy properties or redshift or both. And so comparing the derived curve, which is from this thicker purple line, to the curves that were studied locally and at higher redshift, you can see, although it's sort of a small difference, we're having this notable divergence of the curve in the bluer wavelengths. It's matching more with the redshift 2 star-forming galaxy, so maybe there's some redshift evolution, but the commonly adopted curve is this gold curve. And it's actually starting to differ a little bit. We have to be a little bit careful about the dust attenuation laws that we're applying to these galaxies in the future that have a great impact on what we're measuring in terms of the star formation rate, stellar mass, et cetera, of galaxies. So this is sort of a first stab at making this measurement, especially for high redshift galaxies. And this is, as far as I know, the first time that this measurement has been done for dusty star-forming galaxies in particular. And so one implication of this curve that we've measured is that the dust may be different at higher redshift. Sort of not surprising that it's not the same locally as it is in higher redshift. Maybe indicating smaller dust grains. I think there's a lot of work to be done in this space, and I'm excited for more JWST spectra to be observed so we can do this analysis on larger samples of galaxies. Okay, I said I would come back to this sort of star formation history point. This, I think, is one of the most exciting things about the paper because it's such a stark contrast in what the spectra look like, even though photometrically the 4 galaxies, even with JWST, are completely indistinguishable. And so thinking about the 2 different ways of measuring a star formation rate, we know that they're very star forming on these longer timescales. So if we average over about 100 million years, that is what the far infrared is tracing. So with the sub-millimeter SED, we're tracing these longer timescale star formation rates. All 4 of them have somewhere in the multiple hundreds, few hundred solar masses per year, indicative of this dusty star forming galaxy population. In contrast, while the H alpha derived star formation rates align well with the far infrared, so we're seeing that in this resolved star formation history, these are ongoing starbursts. They're still forming a lot of stars. We can see that in both the optical and the infrared. The galaxy with the Balmer Gregg has a factor of 10 different star formation rate based on these shorter timescale H alpha tracers and the far infrared. So this is a direct constraint of the star formation history in the galaxy and is the first indication that the dusty star forming galaxy population is encompassing multiple evolutionary stages of these galaxies. So they're still showing up as sub-millimeter bright, even though their star formation is shutting down. I think there's a lot of exciting work to be done in this space, looking at larger samples of dusty star-forming galaxies and starting to piece together this evolutionary picture of this galaxy phase. So I want to wrap up the two points from my own work. Using this long wavelength data is an efficient technique to find these high redshift dusty star bursting galaxies and looking at them in detail with spectra. Though they might be indistinguishable photometrically, we're starting to pick up these different star formation characteristics across the sample of dusty star forming galaxies. And looking ahead, we now have this deep multi-wavelength data that we can really leverage for studying massive galaxies, in particular the dusty ones. And I think the next steps for the field are to get volume complete samples and probe the physics in more detail to understand this rapid assembly across cosmic time. Thank you.
Questions for Olivia?
Yeah.
I know you said there was different morphologies in the samples. Do you have any idea what the percentage breakdown or merger fraction?
Yeah. I think it was around a third. I have to look at the exact number. Quite a few mergers, but I think less than expected, maybe some redshift dependence. We'd have to look at Judd's paper for the exact number, but he did do some quick morphology merger rate versus diskiness. And there were quite a few disks, but still like around this redshift peak, still quite a few mergers. Yeah, that grand design spiral is like sort of the like poster child for the mergers. Yeah, it's really cool. He actually put together his own like photometry code because how complex all the morphologies were of these galaxies. Wanted to do something a little more complex than just aperture photometry. So if you go to his paper, you can see he calls it diver for SCUBADive. And it traces like, I think just like an isophote around these like really cool morphologies of these DSFGs. Yeah.
Through a talk on high redshift galaxies and didn't mention supermassive low black holes.
Yeah. I love when people bring up AGN. There's definitely AGN even in these galaxies that I showed. So I didn't mention it, but that is one of the caveats of our measurements that we're making. We cannot constrain the contribution of AGN to these lines, for example, H alpha and N2, completely blended in the PRISM data. And for 2 out of 4 of these galaxies, there's some indication based on the radio excess that there are AGN in the sample. I think having a little more X-ray coverage of the field and deeper X-ray is going to help us a little bit, and potentially higher resolution data spectra for these sources. There's definitely AGN in DSFGs, sort of a known thing. I don't think we have a good handle on the rate of that and how much it's contributing relatively to the different features.
Is it just a small smattering of your objects, or you have no idea are AGN?
Yeah, it's probably more than a small smattering, not all of them, but it's the constraints are a little bit minimal. So we have the constraints from the radio and the X-ray, basically. If we're seeing a radio excess, it's giving us some indication that there's some an AGN there. I think what we don't have a great handle on is how much it's contributing to the rest optical flux. It could be, an obscured AGN in some way, or there was a recent paper showing, basically I think the dust complicates things. How much is it obscuring the AGN? How much is it obscuring star formation? How much is the AGN contributing to these emission lines, for example? Is it making our stellar masses overestimated? I think this is a problem not just for DSFGs, but in general. And once again, that's why multi-wavelength is helpful. But I think this is definitely something to keep in mind for DSFGs. I think, mostly looking in the X-ray and radio is how we're starting to figure that out, but sort of unconstrained relatively in the OIR, how much it's contributing relatively to the star formation, because we know that there's strong starbursts as well. So is the AGN outshining how much dust obscuration is affecting the AGN versus the star formation? I think these are still unresolved.
That iron 2 line is also new to me.
Yeah.
Is it a good metallicity indicator? Do you know?
I don't know in terms of metallicity. I know that it can come from, that's also one of the indications that maybe there's an AGN contributing in the near infrared, although it can also be caused by shocks. So a little uncertain where it's coming from. I know that there's a paper recently using these near infrared lines to as a sort of BPT diagram without BPT lines. So I think of it as connected to either AGN or shocks. But yeah, I don't have a sense of how it can constrain the metallicity. It's not even in, you can see it's like not even in the MSAX, like the model templates. Yeah.